The four fundamental concepts of statistics. Principles underlying inferential stats, as described by Sally Caldwell and a bunch of others who have helped me out along the way. First, census versus sample. Problem is, in most research, a census is not possible. That's why we need to do inference. So for example, finding the mean height of a George Brown student. Try to get a hold of every single George Brown student. That'll be quite difficult. Solution, we estimate the population characteristic with a sample. In exercise 15, we showed that this was not so simple. Only 4 out of 48 of the 6 rolls of the die, 8% were 3.5, which is the correct true mean. This means that almost 92% were incorrect. Problem, we typically don't know the population mean. In exercise 15 we did. Or other characteristic, it could be a proportion, it could be a difference between means, it could be a relative risk, it could be a whole host of other measures. And thus we'd have no idea whether our sample is a good one or a bad one. The solution? Inferential statistics. These symbols will need to be learned by heart. And the key differentiation is between the sample and the population. So sample mean, population mean, sample standard deviation, population standard deviation. Here's a flowchart giving kind of an image of what happened in exercise 15 and what we'll be doing with confidence intervals and with inference. We start off with population, so we have raw scores here. X1, X2, X3, and so on. And some of those get chosen to be part of the data. But there's a whole bunch of other ones that are not. From the data, X1, X2, X3, X4, we calculate the population mean or proportion if it's a single variable, and then we make an inference back to the population. We're estimating back to the population. What happened in exercise 15? In exercise 15, we started out with a population of dice rolls that we knew had a population mean of 3.5. Then we took a series of samples. I'm just arbitrarily calling them 1, 2, 3. So this is one possibility. Person rolled a 2, 3, 4, 6, and so on, and got 3.67 as their sample mean. Another person got 3.33 as their sample mean, and finally a person got 4.5. And so we plotted these on the board and got an upper bound and lower bound generated by SPSS. And if you'll notice, all of these have the upper bound and lower bound on either side of the true population mean, which is 3.5, right? So that's mu. And each of these is one of the X bar 7 or something. It doesn't matter what it is. X bar 7, this is X bar 12. So we can number these. Now there's one of them that missed, but every other one had the true population mean in between the lower bound and upper bound. Now we're starting with the 4 fundamental concepts. The first one is random sampling. In order to be able to make valid inferences about a population, sampling must be done randomly. To choose a sample randomly means that every member of the population being studied has an equal chance of being chosen. So in rolling 6 die, each die has to have an equal chance of appearing. Each individual is chosen independently. All combinations, even the weirdest ones, are possible. So would it be possible for somebody to roll 6 1s, 6 6s? Yes. Second concept, sampling error. Very important one. Most samples will approximate the population, as we saw in the class in exercise 15. Some will be way off because each sample contains only a fraction of the population. Each one will contain some error. Okay, so that's where every one of you, even if you got 3.5, you didn't get the same standard deviation as the population had. So this error is called sampling error, and because of it, we cannot make automatic inferences from sample to population. So we cannot say x bar equals mu. We can use a sampling error to help make inferences. Here's an idea. We're going to take the sample mean, and we're just going to plus minus add the standard error above and below to try to estimate mu. Not a bad start, but we'll see that we need to improve it. Concept 3, distribution of sample means. Imagine that the researcher is able to keep taking samples and calculating the mean for each one. We mimicked this a little bit in exercise 15 as we had 48 samples instead of just one. This will create a set of sample means as follows: x bar 1, x bar 2, x bar 3. The collected and ordered data set containing all the sample means is called the distribution of sample means, which kind of makes sense. And here it is. So with exercise 15, we're going to take each of these sample means now, and we're going to plot it on a frequency table. So this is a frequency histogram. And what will happen is that each value will fall somewhere left or right of the mean, or exactly on the mean. And what you need to think about is that each of these sample means is only one sample from the infinite possible sample means. You can keep going and going and going. So your sample now is just one of an infinite number of possibilities. Concept 4, the central limit theorem. This brings it all together, hopefully. If the population from which the samples are taken has the mean mu and standard deviation sigma, then the distribution of sample means will have mean mu and standard error sigma over root n. And so we see it back here. I'm just flipping back one slide. The prediction is that the population mean will be the mean of the distribution of sample means. As n, the sample size, gets larger, the standard error will get smaller and smaller, right? So as n gets larger, imagine n being 1,000,000 as opposed to 1,000, the fraction will get smaller and smaller. So here we have a distribution of individual raw scores as opposed to, so these are the raw scores, and this is a distribution of sample means. So these m's are x bar. So x bar 7, x bar 15, and so on. And the population mean here is 78. And the population mean here would also be 78. That's what the central limit theorem has been shown. Well, the central limit theorem works, and that's what it says. If one takes a large enough number of samples of n equals 9, or whatever sample size, and plots the sample means, the central theorem predicts that distribution of sample means will be normal with mu equals 78, if that's the population mean, and the standard error of sigma divided by square root of n. and n was 9. The key thing to get out of this is that they're both normally distributed and both have the same mean. When we're shifting from the population distribution to the distribution of sample means, we're making a couple of things. Well, there's a couple of things that need to be remembered. One is normal, normal, mean is mu, mean is mu. Everything else is different. Here we have sigma as a standard deviation. Here we have the standard error. And note that we're using S as an estimate, or sigma. The raw score is X. Here, the raw score is X bar, which is a sample mean. For areas, use Z tables, and for areas under the distribution of sample means, we're going to use T tables, and you'll see how in a sec. Okay, now one step back. This is a really important one. The distribution of sample means is normal. That's a fact you need to learn. And that's true even if the original distribution was not normal. Now, this next part is conceptual in nature, and you don't need to memorize it as much as kind of understand it. 95% of raw scores under the standardized normal curve are within 1.9 standard deviations from mu. 1.9 standard deviations from mu. Remember, Z equals number standard deviations from mu. Take a minute to think about this, but the next slide I think will help. So you can flip back and forth if you need to get your mind around it. So here we have the distribution of raw scores. So this is raw scores. We're back to those. And we have mu equals 78 and sigma equals 6.1. 95% of these raw scores are going to be, so this is one standard deviation, Z equals 1, and Z equals 1.96. And here we have Z equals -1, and Z equals -1.96. What the previous statement has said is that this is 95% of all raw scores. And we know that for sure when we look up, if you trust the Z tables, but the Z tables tell us that 1.96, so we come across here, 1.96, right? So the area between, this is just one side, right? So this is 47.5%, and this is 47.5%. So 95% of raw scores under the standardized normal curve are within 1.96 standard deviations from mu. Okay. Now we're going to change that statement just a little bit. If we choose a random person from the old age home, there's a 95% chance that their age will be less than or equal to 1.96 standard deviations from mu. That's saying the same thing. So remember this idea? Population mean equals a sample mean plus standard error. Well, we're going to refine it a little bit because we're dealing with the normal distribution. And we're going to improve it by saying that the mean is actually, the population mean is a sample mean plus 1.96 times the standard error. And that's based on what we just experienced here. We want a 95% chance that the sample we have is capturing the population mean. So I'm kind of shifting the normal distribution, the raw scores, to the sample mean, sample distribution, the sample means as raw scores, kind of playing with them both at the same time. But if you accept the fact that the central limit theorem is saying that the distribution of sample means will be normally distributed, then it'll work the same way as the standardized normal curve that we worked with last week. But first, so you've accepted that, hopefully. There's a different distribution of sample means for every sample size. Just a touch of complication. This was discovered by a math student working for Guinness Breweries, and it means that we can't blindly use 1.96. That's all. Different sample sizes have different multipliers, as we'll see in a sec. So you have the t-tables with you. Take a look at them. Or if you're doing this at home, online, there's one online you can open up for yourselves. And what you'll see is that, okay, for the standardized normal curve, so these are the raw scores, 1.96, that's what we were using, that's 95%. But if we change, sorry, I'm going to change the color. For blue, we need mu equals x bar plus or minus 2.45 times standard error. And for degrees of freedom 3, which means, sorry, I'm just going to write this out. Mu equals x bar plus or minus 3.18 times standard error. And you can check that out on your t-tables and just confirm that those values are correct, are the same. So here, this is the final formula for confidence interval for means. We have the population mean is being estimated by taking the sample mean and adding the multiplicand or the product of the t-score, which you'll look up in the t-tables and depends on your sample size. Okay, so degrees of freedom here is sample size minus 1. And here we have the sample size, and this is just a calculation of standard error, the calculation in brackets. Okay, so what does this solve for? Well, the confidence interval aims to capture the population mean within a range. So we saw that with exercise 15, where we did that. Once you solve for the unknowns, you'll get a statement like the following. We're 95% confident that mu equals 167 plus or minus 4.5. The interval can be also expressed as a range with lower bound and upper bound. And that's the way SPSS will express it for you. And so then we'd have a statement like, we are 95% confident that the population mean is between 162.5 and 171.5. And it goes back to our basic fundamental of statistics. Statisticians don't say the mean is 4.3. Statisticians don't say the mean is probably 4.3, and we don't say the mean is close to 4.3. All we can manage is the mean is close to 4.3, probably. And we go on and on at great lengths to tell you how wrong we are. Here's just a quick slide showing how Z-score is related to T-score. So there's T-scores that you can use. You won't be calculating anything with them, so you don't need to memorize it or use it. But it's the same idea. So here we have X, here that's the raw score, the same U, and then we're estimating standard deviation for sigma. And you'll also in exercise 18 be working with the confidence interval for proportions. And so here's the formula, and we'll be, this has its own anomalies, but we'll be using 1.96 for 95% confidence every time. Next stage, working on in-class exercises 17 and 18. I hope this has been helpful.